evening, fellow physicists. Now, in the earlier video, we discussed this equation over here. We discussed how operators in the Heisenberg representation evolve in time, in contrast to how Schrodinger operators don't. Now, we are going to see a bit more about the time evolution of the operators in the Heisenberg representation. So let's delve into it. Now, consider taking the derivative of this equation over here with respect to time. What would happen? Let's see. Now we have the time derivative in this way. Now we will take the derivatives term by term. So now we take the first term over here, e to the I ht by h bar, where h is the Hamiltonian. Here I've written h just to denote that we have operator in the Heisenberg representation. It has nothing to do with the physical input here. So now we take the derivative with respect to time. So I, h and h bar would come down because we assume that h is time independent. Hence we have I, h over h bar times, now the exponential would be as it is, so we have I, h t, h bar, as and this is ht, h bar, and this is the operator in the Schrodinger representation. Now we partially differentiated this with respect to time because this could also depend upon other things, but as we know there is nothing to actually take into account the time evolution of the Schrodinger representations operator, but still we would do it just for the crack. So you have e to the I ht over h bar, e to the minus I ht over h bar, and das dt, and finally we differentiate the last term, so we would have minus I h over h bar, e to the I ht over h bar, as, and e to the minus I ht over h bar. Now we see that these two terms cancel out because here I have e to the I ht over h bar, and here I have e to the minus I ht over h bar, and this term is common in all these equations, so we would just write 1 in place of this. So everywhere we would have 1 in place of this, and here as well. So that's 1. Now we can rewrite this equation. So we have, now I and h bar are constants, but Hamiltonian is actually an operator, so I could write h a, and now I could give it a hat just to denote that this is an operator, and I could take this minus 1 over here, and we'll see why, and minus I h bar. Oh, sorry. Now here you would have a h, and finally we would have das over dt. Now we can take the I h bar common out here, so we would have I h bar h a minus a h plus d as over dt, and now we see that this thing over here is actually a commutator because we have an operator acting upon another operator, and we have the same thing but in reverse. So this is what emphasizes a commutator. So I have I h bar times the commutator of h and a, because h comes first over here, so we have h a plus d as over dt, and this thing over here is actually equal to the total time derivative of the operator in the Heisenberg representation. So in general, for any operator in the Heisenberg representation, the time evolution is governed by this equation over here. Now actually we know that the das by dt has no sense in the general case because operators in the Schrodinger representation don't depend upon time in the very general case. So hence we are left with this equation over here, and this equation is known as Heisenberg's equation. Heisenberg's equation. And this equation actually is the epitome of the Heisenberg representation. It's like the Schrodinger equation for the Heisenberg representation. Its importance is at that level. So hence we would like to conclude with saying that this equation over here would be very similar to something which we will discuss in the next video with respect to Poisson brackets. But here we see how commutators naturally evolve in quantum mechanics. They also commutators are something inherent in quantum mechanics. We cannot do quantum mechanics without commutators, but this is something which is very interesting, as we will see in the next video. If you liked it, please share it with your friends, and thank you.